So, we are studying quantum mechanical treatment of single electron system or hydrogen like atom So, in last class we have shown how to solve the Schrodinger equation for hydrogen like atom, and whatever result we got, that today I will discuss on the result. So, what we have seen basically one has to write Schrodinger equation in spherical coordinate, and then we have to use separation of variable method. So, this Schrodinger equation is a wave function of r theta phi and then separation variable method. So, this we have taken three independent function of r, theta and phi, and then using this separation of variable method, one has to separate the equation and we will get three equation. So, one is phi equation, another is r equation and theta equation. Okay. So, this we have these three equation. Now, we have to solve this equation and we will get the wave function phi, r and theta. Okay. So, how to solve that without details calculation, I have shown you that the solution of phi equation. So, this is the standard second order differential equation and its generally solution, standard solution is this. Okay. And for normalization one can find out this value of A. So, this A value is 1 by square root of 2 pi. Okay. So, here you can see that is one constant ml it has come during separation variable method, and this ml is basically it from boundary condition one can show that ml can take value minus L to plus L, and what is L, that has come from the next theta equation. So, this during solution of theta equation, so this variable L constant, not variable, constant L came in, and the solution of theta equation is basically in terms of, this is in terms of associated Legendre polynomial, and this Legendre polynomial, that is form of this Legendre polynomial is basically this is associated Legendre polynomial and this Legendre polynomial. So, when PL function of z, so then it is the Legendre polynomial, then it is associated with ML. So, that is the associated Legendre polynomial. So, here this polynomial are basically this standard form of different kind of polynomials. So, Legendre polynomial is one of them. So, I will I will tell you about these polynomials. So, here we have got this theta equation, theta solution in terms of Legendre polynomial or associated Legendre polynomials. Okay. So, and finally, this solution of R equation, and in that case is its solution is in terms of associated Laguerre polynomial. Okay. See, this is another polynomial. It has standard form, and from basically from mathematical physics one learn this different kind of polynomials. And this here we have taken solution for E is less than 0. This is basically for bound state. If E is greater than 0, so this it is called scattering state, is the unbound state. Okay. So, but here we have only considered the bound state. So, solution is valid for E is less than equal to 0. Okay. And the solution we got, that is RNL function of R, that is in terms of associated Laguerre polynomial. And in this during this solution, we got the energy expression E n, that is basically minus mu z square e to the 4 by 2 n square h cross square, 2 n square h cross square, and which is exactly same as the Bohr as the energy we achieved from the Bohr model. And also here we have considered this A 0, this Bohr radius, that is h cross square by mu e square. Okay. So, this result generally one can, we use this Bohr radius in terms of Bohr radius A 0, one can express this radial terms. Okay. And one has to normalize, then one can get this value of C, and this normalization, this one has to this follow the procedure, normalization procedure. Okay. So, R star R and this R square dr. Why R square, that I have explained. Okay. So, this elementary volume, it is basically R square sin theta d theta d phi, this is the volume elementary volume. Okay. So, from there basically this R square come, and using this normalization value one can write complete solution for radial part in terms of Laguerre, associated Laguerre polynomial. Okay. So, here this polynomial just we are writing in terms of polynomial, because these are the standard polynomials we learned from mathematical physics, and what are the characteristics of this polynomial, that is also from chart, from table one can find out for different value of n and l, what are the polynomials, what are the exact value of the polynomials for that n and l. So, that one can get from the table. So, so finally, after solving this Schrodinger equation in spherical coordinate. Okay. So, what we achieved? We achieved basically energy E n equal to minus mu z square e to the 4 by 2 n square h cross square. So, that was basically we achieved from the Bohr model. So, after this tedious calculation using this Schrodinger equation, we are getting same result as we got from the Bohr model in terms of basically in case of energy. So, why should we do this tedious calculation. One reason is that in Bohr model, so on ad hoc basis, on assumption basis, there are many things we considered, but from quantum mechanics, from quantum mechanical treatment, that same things has come automatically in natural way. Okay. So, we have not considered, we have not assumed anything. So, it has come in natural way. So, this is one. Another is, so Bohr model, basically their energy expression we got fine, and in this quantum mechanical treatment we got the same energy, but in quantum mechanical treatment we are getting additional things, that is the wave function. Okay. So, we got the wave function for the hydrogen like atom. Okay. So, these the additional things we got. Now, this wave function basically contains all information about the hydrogen atom in this case. So, one has to now what information, what are the information, how to extract those information from this wave function, that one has to know, and one has to interpret this wave function to get defined information about the hydrogen atom. Okay. So, basically here we have got wave function, that is for phi dependent phi ml. Okay. So, this is e to the power I ml phi. Okay. So, this other part, this is the normalization part. So, if I drop this normalization part, so this is the e to the power I ml phi, that is the wave function, and then theta, capital theta, it is a Lm, theta Lm function of theta. So, here it is a this wave function is basically this associated Legendre polynomial. Okay. Where L equal to, here L is involved, L is involved. Okay. So, here basically this is ml. Okay. So, this L value is 0, 1, 2, 3 up to n minus 1, and this orbital angular quantum number ml is value 0, plus minus 1, plus minus 2 up to plus minus L. So, this is the magnetic quantum number, and then this another function RNL as a function of R. So, this function is basically, this the normalization part is there. So, if we forget it, drop it. So, it is basically this function is exponential, it has one exponential term e to the power minus z r by n a 0. Okay. And then it has r dependent r to the power L, this other constant terms are there, 2 z n a 0 r to the power basically L, and this then this associated Laguerre polynomial. So, for details wave function, so one has to know what is associated, what is the form of associated Legendre polynomial, what is the form of associated Laguerre polynomial. So, that one has to know from mathematical physics, and these are standard, there are standard wave function polynomials one. So, that from mathematical method one can get of this polynomials. One is Hermite polynomials, harmonic oscillator, for harmonic oscillator. So, the solution comes in terms of Hermite polynomials. So, this is the definition. So, this is the polynomial is written h n x, that is equal to minus 1 to the power n exponential x square, and then d n by d x to the power n exponential minus x square. Okay. So, this is the Hermite polynomial. Okay. This basically Hermite polynomial, and this is the solution of this differential equation of this d2 x n by dx square minus 2 x d n d h n by dx plus 2 n h n equal to 0. So, if your differential equation form comes like this, then its solution is this h n, okay, and h n, this form is like this. Okay. So, so these are the ready made things available in mathematical physics, mathematical method. Okay. From there one has to pick up this this solution, and this, in as I told, in table generally you will find out this polynomials for different value of n, l, m, l. So, in this case it is h n is independent. So, for n equal to 1, this h n x is 1, h 1 that is 2 x, h 2 that is 4 x square minus 2. So, these are the form of these Hermite polynomials for different value of n. Okay. So, that will be available from the table, okay, in mathematical method, and this polynomial generally satisfy some relation. So, like it follows the orthogonality relation. What is orthogonality relation? That is defined. Okay. It follows the recurrence relation. Okay. So, these are the characteristics of these polynomials. Okay. So, similarly, so you have Legendre polynomials. So, definition of the Legendre polynomials. So, these are basically P L x. Okay. This is the form of these Legendre polynomials, and corresponding few Legendre polynomials having different value of L. So, P 0 L equal to 0. So, this P 0 is 1, P 1 is x, P 2 is half 3 x square minus 1. So, these are the form of polynomials, Legendre polynomials for different value of L. Similarly, it follows the orthogonality relation. So, these are the here just I am showing. So, these are the standard, it is available in mathematical method, and you will get these all characteristics and different term for different value of say in this case L. Okay. In case of associated Legendre polynomial, it is in terms of Legendre polynomials. So, P L m x, this is a square root of 1 minus x square to the power m d m by d x to the power m P L x. So, this is the Legendre polynomials. So, then this is the associated Legendre polynomials. So, already P L x we know, P L x we know. Okay. And these the associated Legendre polynomial, this is the solution of this kind of differential equation. Okay. So, when we are solving the hydrogen equation, okay, so Schrodinger equation. So, in that case always we try to take the equation in the standard form, in the standard differential form, so that its solution is readily available. So, so in case of radial part, so this Laguerre polynomial, in case of theta part. Okay. So, that is the Legendre polynomial. Okay. So, so this here just from table I have written what is the value of P L equal to 1 and M L equal to 1. So, what will be the value? So, that is the square root of 1 minus x square P 2 1 function of x, it is the 3 x square root of 1 minus x square. Okay. So, these are the few associated Legendre function for different value of L and M L. Okay. And it also follows this orthogonality relations. This Legendre polynomial also satisfy the orthogonality relation. Okay. Similarly, this another important polynomial, that is Laguerre polynomial. So, this Laguerre polynomial is form is this e to the power x d L by d x to the power L of x to the power L e to the power minus x. Okay. So, this is the form of Laguerre polynomial. So, associated Laguerre polynomial is basically in terms of Laguerre polynomial. Okay. So, dm by dx to the power m of Laguerre polynomial Lx. So, this is basically this polynomial is the solution of this differential equation of this form. So, in case of radial, so we tried hard to get the equation in this form, then because we know this, if we convert the equation in this form, then we have ready made solution. Okay. So, that is associated Laguerre polynomials, that solution. Okay. And first few associated Laguerre polynomials, so that is available and we can get from the table. Okay. So, like L equal to 1 and ML equal to 1. So, that is equal to minus 1, L 2 1, that is 2x minus 4. Okay. Similarly, L 2 2 means L equal to 2 and M equal to 2. So, in this case, so it is 2. So, these are the different polynomials for first few values of L and ML. Okay. So, these are the here just standard things. So, we have to use them and we should get we should find out the solution for a particular physical system. So, in case of harmonic oscillator, so solution in terms of Hermite polynomial. In case of hydrogen like atom, the solutions are in terms of Legendre polynomial, Laguerre polynomial or their associated form. Okay. So, now as I showed you that we have complete solution in our hand. We have complete solution in our hand. So, this is the Schrodinger equation, and for that Schrodinger equation, putting all boundary condition, we got the physical form of this wave function. So, that is that psi, it depends on n, l and ml. Okay. And it has 3 parts, and this r, theta and phi, and their form of these 3 parts, these 3 wave functions of phi, theta and r. So, that is we have written here. Okay. So, this solution is in our hand. Okay. Now, as I told you that solving this Schrodinger equation, we got this the energy expression, but from Bohr model the energy expression we got, that is this, and also radius of orbit from Bohr model we got this r equal to n square a square by mu z e square. Okay. So, but so far this what will be the r, what will be the whether any equivalent parameter is available from the Schrodinger solution in case of Bohr orbit. So, that answer we cannot give right now. For that we have to go further. Okay. So, so far from Schrodinger equation we got the energy expression, which is same as the expression got from the Bohr model. Bohr model, what will be the radius of the orbits, that expression is available, but whether similar information we get from the Schrodinger equation, Schrodinger solution for this one electron system or hydrogen like atom. So, that we have to wait. Okay. And basically in next I am going to tell about this. So, here as I already told, what are the additional benefit we get solving the Schrodinger equation. So, that is additional benefit, as I mentioned, that is basically Schrodinger, that is eigen wave function. Okay. Wave function. Now, eigen wave function, when this type of equation we write this type of equation, we write H psi here. If we psi now we have right form psi n l m l. So, psi n l m l equal to, we can write E n psi n l m l. Okay. So, this form we write. So, this we tell this Schrodinger, there is the eigen equation, and then psi n l m, that will be eigen function, and E n energy, that will be the eigen value of this equation. Okay. So, solving the Schrodinger equation, we got the additional things, that is eigen function, and that eigen function is psi n l m. Okay. Now, as I mentioned, one has to extract valuable information about the properties of the atom from this eigen function, and how to do that. So, that I will discuss in next class. So, I will stop here. So, thank you for your kind attention.